Hi. Today we're going to calculate the integral from 0 to infinity of log of x over 1 plus x squared dx. And we're going to do it in two different ways. One of them I call the easy way, and one of them I call the hard way. Well, let's first do it the easy way. So, the integral from 0 to infinity of log x over 1 plus x squared dx, we're going to separate this into two integrals. So this equals the integral from 0 to 1 of log x over 1 plus x squared dx, plus the integral from 1 to infinity of log x over 1 plus x squared dx. Now in the first integral, let's do our u substitution. We'll let u equals 1 over x, so therefore x equals 1 over u, which implies dx is minus 1 over u squared du. Plugging this data in our first integral, and we come up with the integral now from infinity to 1 of log of 1 over u all over 1 plus 1 over u squared times the quantity minus 1 over u squared du, and plus our second integral here, which we just brought down. We haven't changed that. So now this equals minus, which is the minus from our dx term here. So it's minus the integral from infinity to 1 of minus log u, which is simply using logarithm rules on the log of 1 over u, over u squared plus 1 du, plus our second integral again. And now we have a minus and a minus. They cancel, but we're going to flip the limits around, which will bring out a minus. So this equals minus the integral from 1 to infinity of log u over u squared plus 1 du, plus the integral from 1 to infinity of log x over 1 plus x squared dx, which of course equals 0. These two terms just simply cancel each other. Okay, well that was a fairly easy method. just separating the integral into two integrals and doing a u substitution in one of them, and we find that they neatly cancel each other. Okay, but I would like now to show you another way, and it's quite a bit harder, but it'll give you an idea of a way which could be very profitable for you and other integrals. I don't know if you would call it a trick. That word is used much too often, I believe, in math. But it is clever. And what we're going to do is use residue theory here. And you notice this integral that we want to compute is log x over 1 plus x squared. And that's what we're going to compute again. But this time we're going to let f of z equals log of z squared over z squared plus 1. Notice we're squaring the log here. And we'll find out why. We're still going to calculate this integral, the log x over 1 plus x squared, but we're going to use the function log z squared over z squared plus 1. Okay, since we have a log z here, we're going to have a branch point at z equals 0, of course. And we're going to choose our branch cut to be the non-negative real axis. In other words, 0 is less than or equal to x is less than infinity will be our branch cut. Okay, let's continue. Well, I made a picture here of the path we're going to use. And it'll be, a typical path that's used in complex analysis. And I'm calling this big semicircle, or this big circle almost, I guess you'd call it. I'm going to call that capital gamma. Name the path as capital gamma. And this little circle here, I'm going to name that path little gamma. It's all kind of messy in here, but you'll see what we're doing. And we're going to have two straight line paths. The one that goes from R to epsilon, I'm going to call that delta sub B, just on the bottom of the axis there. And the path on top of the axis, from epsilon back to R, I'm calling that delta sub T. So let's kind of trace out what we're going to do here. Well, let's start right here at capital R on the x-axis. We're going to go around gamma here all the way to minus R. This is supposed to be a circle, by the way. And it's going to come all the way up to positive R again, at which time we're going to transfer to delta sub B along the bottom of the axis all the way down to epsilon. Then we're going to hitch a ride on little gamma and go around another circle all the way back to epsilon, where we're going to transfer again to delta sub T along the top of the real axis. Okay, let's first look at the integral around capital gamma, the big circle. And for right now, we're going to assume capital R is bigger than 1. And we're going to make a substitution here. We're going to let Z equals R e to the I theta, where theta goes from 0 here all the way up to 2 pi. And so then our dz will equal IR e to the I theta d theta. And for this, we're going to start looking at the absolute value of the integral over capital gamma. Well, let's rewrite that. That's the absolute value of the integral over gamma of the log z squared over z squared plus 1 dz by the definition of our f of z. And substituting our thetas in there for z's, this will equal the absolute value of the integral from 0 to 2 pi of the quantity log of r e to the I theta squared over r squared e to the I 2 theta plus 1 in the denominator times IR e to the I theta d theta. That's just our dz right there. Okay, multiplying some of this out, this is equal to the absolute value of the integral from 0 to 2 pi of the quantity log r plus I theta all squared over, again, r squared e to the I 2 theta plus 1 times IR e to the I theta d theta. Okay, now bring in the absolute values on the inside. This is going to be less than or equal to the integral from 0 to 2 pi of the absolute value of, finding the modulus of this and squaring it will be log of r, quantity squared, plus theta squared, over the absolute value of r squared e to the I 2 theta plus 1 times r d theta. Of course, the absolute value of I and the absolute value of e to the I theta are both 1. Well, now this is going to be less than or equal to the integral from 0 to 2 pi of, again, the numerator is log of r squared, plus now, what's the biggest theta can be? It's 2 pi. So the biggest that theta squared can be is 4 pi squared right there, divided by r squared minus 1 times our r d theta. Now why is this here, r squared minus 1? Well, you'll be able to see that since the absolute value of some a plus b will be greater than or equal to the absolute value of the absolute value of a minus the absolute value of b, where a and b are complex numbers. This is a familiar result. And so, calculating this now, this simply equals, these are all constants in here, so it equals log r, quantity squared, plus 4 pi squared over r squared minus 1 r, now times the integral of 1, which is 2 pi. Which, of course, as we know, we can tell very easily, this goes to 0 as r approaches infinity, because this r squared is going to dominate the r and also the log r squared. Therefore, we can say the limit as r approaching infinity of the integral over capital gamma of f of z dz equals 0. All right, let's continue. Let's look at the integral over little gamma now of f of z dz, actually the absolute value of it. And now for this, we're going to let 0 less than epsilon is less than 1 for right now. And again, we're going to choose our z equal epsilon e to the I theta, as theta starts at 2 pi and goes down to 0. Of course, we can see that with our picture here. Theta start at 2 pi here and go all the way around this direction, as it must, all the way down to theta equals 0. Okay, then dz will equal I epsilon e to the I theta d theta. And therefore we have the absolute value of the integral from 2 pi to 0 of the quantity log epsilon plus I theta squared over epsilon squared e to the I 2 theta plus 1 times I epsilon e to the I theta d theta. This is just our dz. And again, separating the logs here into the real and imaginary parts. Okay, just as before, we're going to bring in the absolute value signs. So this will be less than or equal to the integral from 0 to 2 pi of log epsilon squared plus 4 pi squared over 1 minus epsilon squared now, times epsilon d theta. Now, since epsilon is between 0 and 1, this will be a positive quantity down here. Just using that same relationship of the inequality as we did before. All right, well, all these things are constants in terms of theta. So we're just going to be integrating 1 from 0 to 2 pi, and that'll leave us log epsilon squared plus 4 pi squared over 1 minus epsilon squared times epsilon times 2 pi, which approaches 0 as epsilon approaches 0. Why is that? Well, we have an epsilon here, and that'll dominate the log epsilon squared and the 4 pi squared. It'll shrink much faster than these things will either blow up here in this case, and then a constant will remain the same. And the denominator is no problem, that just goes to 1. Therefore, we can say that the limit as epsilon approaches 0 of the integral over little gamma f of z dz equals 0. Now, let's concentrate on the last two pathways. First, we're going to look at delta sub b. Remember, delta sub b was at the bottom of our branch cut, going from r to epsilon along the x-axis. And so the integral over delta b of f of z dz will equal the integral from r to epsilon of the quantity log of x e to the I 2 pi squared over x squared plus 1 dx. Well, where did this e to the I 2 pi come from? Well, of course, we're here at the bottom of the branch cut, and the angle of that, remember, we're using the branch cut from 0 to infinity, and we're using the principal branch, of course, which starts at 0, comes all the way around here. Here we're at pi, 3 pi over 2, and all the way up to 2 pi, just underneath the branch cut. And that's where that e to the I 2 pi comes from. Okay, multiplying the numerator out will give us the integral from r to epsilon of log x squared plus 2 log x I 2 pi minus 4 pi squared all over x squared plus 1 dx. And let's just leave that for a moment and look at the delta sub t integral. Delta sub t is the top of the branch cut, and its angle will be 0. And so the integral over delta sub t of f of z dz will equal the integral from epsilon to r log x squared over x squared plus 1 dx. Okay, well, let's combine these two integrals, the one over delta b and the one over delta t, and add them together. And at the same time, we're going to change this delta sub b integral. We're going to flip the limits here, so that'll bring out a negative sign. So this will equal the integral now from epsilon to r of minus log x squared minus 2 log x I 2 pi plus 4 pi squared, just plugging in a negative sign in each of these terms, and plus log x squared, which comes from our delta sub t integral, all over x squared plus 1 dx. All right, well, simplifying that, we get the integral from epsilon to r of 4 pi squared minus 4 pi I log x over x squared plus 1 dx. And let's separate this into real and imaginary. This equals 4 pi squared integral from epsilon to r of dx over x squared plus 1 minus 4 pi I times the integral from epsilon to r of log x over x squared plus 1 dx. Notice this thing here is getting very close to our target integral. All right. According to residue theory, the integral of our f over gamma plus the integral of f over little gamma plus the integral over delta b plus the integral over delta t will equal 2 pi I times the sum of the residues of f that are inside our path. Now, in this case, f of z has two first order poles. One is at I and one is at minus I. Coming from the bottom here, the denominator, where z squared plus 1 equals 0. So let's calculate those residues. First at I, the residue of f of z comma I will equal z minus I log z squared over z minus I, z plus I, where z is approaching I. And We have some cancellation there, which is nice. And this will bring 1 over 2I times the log of, well, the log of I, but the I can be written, in this case, e to the I pi over 2, quantity squared. Remember now, we're in the principal branch, so I equals e to the I pi over 2. And simplifying that, this equals 1 over 2I times I pi over 2 quantity squared, which equals minus 1 over 2I times pi squared over 4. Okay, now let's find the residue of f at minus I. This will equal z plus I log z squared over z minus I, z plus I, where z approaches minus I. And this will equal minus 1 over 2I times the log of e to the I 3 pi over 2 quantity squared. Now why is it 3 pi over 2? I 3 pi over 2 instead of minus I pi over 2? Remember, we're in the principal branch, so we go around the circle and counterclockwise, and we reach I 3 pi over 2. Well, simplifying that, we get minus 1 over 2I times the quantity I 3 pi over 2 squared, which will equal 1 over 2I 9 pi squared over 4. So, we can finally say now, we want epsilon to go to 0 and we want r to go to infinity. We can say that the limit where epsilon goes to 0, r goes to infinity of the integral over big gamma plus the integral over little gamma plus the integral over delta b plus the integral over delta t will equal 2 pi I times the residues, which is 2 pi I times 1 over 2I times the quantity minus pi squared over 4 plus 9 pi squared over 4. These two residues here that we found. All right, well, let's bring this thing home now. We found out earlier that the limit as r goes to infinity of the integral over big gamma was 0, so we'll put a 0 there for that. And we also found out the limit as epsilon goes to 0 of the integral over little gamma also was 0, so let's bring that down 0. And we just found out that the sum of these two, the integral over delta b and delta t, added together, we found that was this quantity right here. So let's bring that down. 4 pi squared times the integral from 0 to infinity of dx over x squared plus 1 minus 4 pi I times the integral now from 0 to infinity of log x over x squared plus 1 dx. So as epsilon goes to 0, that's where we get the lower limits, and as r goes to infinity, that's where we get the upper limits. And this equals to 2 pi cubed, which is the simplification of 2 pi I times our residues, the sum of our residues. Okay, well, this integral right here is well known. The antiderivative is arctan of x, so we have arctan of infinity minus arctan of 0, which is pi over 2. So we have 4 pi squared times that pi over 2, then bringing this down, minus 4 pi I times our target integral, 0 to infinity, of log x over x squared plus 1 dx will equal the right hand, which is 2 pi I times the sum of our residues, which is 2 pi cubed. Well, let's calculate this out. Here we get 4 pi squared times pi over 2. Well, that's 2 pi cubed as well. So bringing this 2 pi cubed over to the right-hand side will give us a 2 pi cubed minus 2 pi cubed, which will be 0. At that point, we'll divide by minus 4 pi I, so the right-hand side will still be 0, and that'll leave our target integral, which is the integral from 0 to infinity of log x over x squared plus 1 dx, is, of course, 0. The same result we got using the easy way. And you might ask, well, why did I even bother with the hard way if I already knew the easy way was going to be much simpler? Well, I just wanted to show you this method. This method could be very useful. For instance, if you had analytic functions in the denominator, like polynomials or other analytic functions, and you wanted to go from 0 to infinity, simply by multiplying by log x in the numerator, you could create a branch cut from 0 to infinity, and the log x will disappear when you do that. Or if you started with some power of log x in the numerator, as we did in this case, we started with log x, multiply it by another log x, and then the highest power of the log x will disappear, leaving lower powers of log x, which presumably you would know already by doing the process earlier. And I hope you enjoyed this video. And if you did, maybe you could give it a like. Thank you very much.